All right, so in this batch of problems, I want to show not just the one in the card here, B3, but I'll do 3 out of the 4, and I'll leave the 4th one for you guys to do as a homework problem. The setup for this problem says we have a field F, characteristic of F not equal to 2. We have two elements A, B in F, and they should be different. And I don't think Pinter says this. I'm not 100% sure if it's important, but I feel like I should throw in non-zero as well. I don't know how much that may mess things up. I didn't think about it all the way, but it feels like it could be a bit of a problem. So let's just assume A and B are non-zero. Surely the problem is easy if one or both of them are 0. So it seems like a good assumption. First comment I want to make is what's going on with this? Characteristic often has specific elements that, like specific prime numbers that it doesn't want to be, frequently 2. And it happens a lot when you want to square things or just in general work with powers. But squares makes it really clear what's going on. Because how many times have we explained to our students that this isn't true, right? Squares, they don't work. You got the cross terms, right? What you actually get is a squared plus 2ab plus b squared. But wait, if the characteristic of f is 2, yeah, that's not good, right? Or maybe I shouldn't say it's not good because this can sometimes be interesting or even a helpful phenomenon. But in general, exponents will not play nice when the exponent is p if the characteristic is p. And so in this problem, since we want to be talking about squaring a whole bunch, we're going to insist that the characteristic of f not be 0. Or sorry, not be 0, not be 2. Now, for our problem, we assume further that f contains square root of a plus a square root of b. I want to show that if f has square root of a plus square root of b, f also has just square root of a, just square root of b, individually. And here's how we can do that. So I start by taking square root of a, square root of b, and since it's the field element, I can square it. And I get a plus 2 square root of a, 2 square root of b, plus b. Since this is a field element, a and b are also field elements, I can subtract them. So that means 2 square root of a, square root of b is an f. Since the characteristic of f is not 2, I'm allowed to divide by 2 and see that this is an f. But you see, since this is an f, so is square root of a, square root of b times square root of a plus square root of b, which is equal to b square root of a plus a square root of b. And we're almost done now. The key is that since a and b are different, if this element is in the field, so is what I can get by subtracting off, for example, b square root of a plus square root of b, because b is in the field and we assumed this is in the field. But now this cancels with this, leaving a square root of b minus b square root of b, which is a minus b square root of b in f. And since a and b are different, this is not 0, so I can divide by it. That gets me square root of b in f. You can reverse this logic at this critical step here to also get square root of a. Not reverse it, but like turn it around, right? So because subtract off a times that stuff instead to cancel the other guy. Okay, that handles the first part. Actually, wait, not quite. There was one last bit, which was to conclude. We were to conclude that f adjoin square root of a plus square root of b equals f square root of a square root of b. We haven't seen too much of this yet, but it's oftentimes the case where when you have some kind of more complicated field extension, you want to work out a basis. You don't always know, like, are there possibly interactions between the things that might make it so that the degree of the extension isn't the full degree that you would expect if you just look at the individual components. This shows us that under these assumptions, right, I have two different non-zero field elements and a characteristic not equal to 2. the sum, it works out nice. And so why is this? Well, clearly, since square root of a plus the square root of b is equal to 1 times the square root of a plus 1 times the square root of b, clearly we have f square root of a plus square root of b contained in this guy. What we just proved is that the opposite is true, right? Because once I can get square root of a and square root of b individually in this thing, of course, I already have all the constants. They have the same constants. So if I can get this to be in here and this to be in here, which we did, then the reverse is true. So they're equal. Okay, very cool. Next part is to prove that if b is not equal to x squared a for any x in f, what does he ask me to prove? That square root of b is not an element of f adjoins square root of a. And when I see this, I see two statements here that are both negated. So I think to myself, contrapositive, right? So contrapositive says that if square root of b is in f adjoins square root of a, then b is of the form x squared a for some x. So that's kind of telling me what to do here, right? It's saying I start with this assumption that square root of b can be written in this thing, and then I try to write b in the form of this. Well, how do I write this? We know that f adjoins square root of a, since a is a field element, right? Square root of a obviously satisfies square root of a squared minus a equals 0, so it's degree 2. And so the basis is given by the 1 of f, so I can call that c, right? I need some constant term, plus some multiple of the non-trivial element being added. Now I got to work this so I can write b equals x squared a. Well, the simplest way to get b out of this is to square both sides. b is equal to c squared plus 2cd square root of a plus d squared a. Now, this doesn't look like it's in that form yet, but I know that I have to get an a out on the end eventually. So I'm going to factor out an a since a is non-zero. And you notice I'm allowed to do this because square root of a is also non-zero, so I can divide by it. So now the question is this a perfect square? The answer is, of course it is, because this thing was a perfect square, and what I factored out was a perfect square, because a is the perfect square of the square root of a. This is c over square root of a plus d squared a. And you will notice all of these are perfectly good field elements, since c and d are field elements by assumption, and since a is non-zero, square root of a has a reciprocal. So we did it. All right, third part's kind of annoying, except luckily for us, Pinter does a little bit of hard work for us to help us out. He says, let's now consider the expression square root of a plus square root of b one more time. And in particular, he says to show that x satisfies x to the 4 minus 2a plus b x squared plus a minus b squared equals 0. And then he asks us to show furthermore that x equals the square root of a plus b plus 2 square root of ab also satisfies this equation. And therefore, to conclude that f adjoin this mess is equal to f adjoin the iterated extension square root of a square root of b. So this is a sort of a, this part's kind of like a multiplicative version of what we just saw. Or maybe not. Maybe that's not the right way to think about it. I don't know. An iterated extension involving this more complex, kind of degree 4 looking thing. Okay. In any case, let's just check that, right? Like, to do this without knowing what the solution is feels like it would be a huge pain. But since I know what I'm dealing with, let's just plug this stuff in and see what we get. So for x, I got square root of a plus square root of b to the 4th power minus 2a plus b square root of a plus square root of b squared plus a minus b squared. And let's just get to work, right? For this first thing, we get, it's binomial theorem, right? So I have a squared plus 4, this becomes a to the 3/2 power, square root of b, plus 6ab, plus 4, square root of a, b to the 3/2 power, plus b squared, minus 2a plus b. What's this thing? This thing is a plus 2 square root of a square root of b plus b. This last guy is a squared minus 2ab plus b squared. All right, so we have quite a bit of mess here. We have to start looking for things that might cancel out, or at least like terms that we can group up. And so here I see an a squared and an a squared, and some ab's, and some ab's, and some b squared, and some b squared. So with the a squareds together, we get 2a squared. Next term stays the same. Here we got 6ab. Here we got minus 2ab. So that's 4ab. 4 square root of a, b to the 3/2. And then I got b squared, and b squared is plus 2b squared. And that leaves this stuff. And since I know I'm trying to get 0 here, I feel inclined to factorize this in some clever way rather than multiply this out and then see that everything cancels. So I see the 2 in front. I see all my 2's here. 2a squared plus 2a to the 3/2 square root of b plus 2ab plus 2 square root of a b to the 3/2 plus b squared minus 2a plus b, a plus 2 square root of a square root of b plus b. All that stuff stays the same. All right, so now let's see if we can do some factoring by grouping. It's our favorite thing. I'm pretty sure I can. Let me check a little bit further. I feel good about this. All right, let's show you the trick. What I'm going to do is split the middle guy in half. Yeah, all this stuff stays the same. I have half a mind to stop writing it because it's only there for comparison. Now, I'll take an a out of the first ones. And so then what remains is, 2 square root of a square root of b plus b. And now I'll grab a b out of this guy. A plus 2 square root of a square root of b plus b. All right, and I'm done. This is the same, right? I didn't change it, but you'll notice here I have a plus b, which is this, and I have this, which is this, so it equals 0. Whew, hard work. All right, I had to do one other one though, which was to take the same polynomial. So we're going to copy and paste it. And then I got to look at this thing also. I don't think this guy is as bad. Because it's just one big nested square root. I think it's probably easier. But who knows? Maybe famous last words. So when I plug this in, first things first is I get a plus b plus 2 square root of ab squared, right? This is squared squared. The first squared gets rid of it. The second squared stays. Minus 2a plus b. Again, I can cancel. I can cancel the outer radical. And I need to see that this minus this equals 0. And this just, it doesn't look that bad. I think we can do it. Let's see. This becomes a squared plus 2ab plus 4a times the square root of ab. That might not be the best way to write it, but it's what I'm doing for now. Plus b squared. And then I already did a and b, so now I got to do 4b times the square root of ab, and then plus 4ab. That's the expansion of this. All right, and sorry, I'm just a little unhappy because unless I copied this down incorrectly, it seems like something is a little bit awry because this has 2a and then it's going to hit into this a and give me a 2a squared. But I only have 1a squared. So how could this be? Oh, because I forgot the last term, which is a minus b, and also the squared got cut off. So that's gonna fix it for sure. Because that is a squared minus 2ab plus b squared. Okay, now it makes sense. Gotta copy and paste with care, friends. Okay. Well, I shouldn't have rewritten that because I didn't copy down everything else. This was just the expansion of this part. And we're kind of hurting for space, so I'm going to try to write it nice and squeeze a little. And now I think we are safe to once again look for things to collect and possibly cancel. We have a squared and ab's and b squareds. And ab's. Wait, where did this come from? From this thing squared. Okay, never mind, it's fine. And then all of these things, a squareds, ab's, and b squareds. So how many a squareds are there? A squared, and then over here, another a squared. So I have 2a squared. How many ab are there? 2ab minus 2ab. So there's just 4ab. Let's scratch these out when we're done with them so we don't accidentally recopy them. This, and this, and this. And then for the b squareds, I have b squared plus b squared. So that's 2b squared. Okay, now let's take down the stuff that remains. 4a square root of ab plus 4b square root of ab, and then minus this expression in its factored form, which is just like before, a useful hint for what to try. So I see again, I have a 2 out in front, so let me take care of that. And now let's look for any factoring tricks that might work on this to see that this is the same as this. Probably factoring by grouping will once again save the day, especially in light of this thing having a square root of AB, this thing having a square root of AB. Like maybe we can break some things up. What I will need, right? I mean, of course, I could also go the other way. I could just expand this and see that they're the same. And actually, I think I'm realizing that that's easier. So let's do that, right? I feel like at this point, there's no way this video hasn't gone on entirely too long as it is. Yikes, 21 minutes. Okay, let's wrap this up cleanly. Here I have a squared. Here I have a squared. Here I have AB. Here I have AB. I need to take a little bit of care to make sure that things have the right coefficients. So here I have the 2's factored out in front for each of them. And so here I get a contribution of a single AB, but here I have another AB, right? And so together, that's everything. For the B squared, that's this guy. And that handles the usual FOIL stuff, right? I only need to then look at what happens with the third term. And there's an A and there's a B. 2A square root of AB is 2A square root of AB, and the same for B. So then these things hitting onto that thing give those. So it equals 0, as we said. Whew. All right. This has been hard work, friends. I'm going to stop this here now. Your homework problem, one of your homework problems, is to finish this with part 4, which says to use the discussion that we've done to come up with a simple basis for a complicated field extension. And so I think this is a great problem in terms of calculation, like learning to apply what we've done to come up with simple ways of talking about complex fields. Not in the sense of complex numbers, but just generally complicated. And so I will leave that to you to finish off in great style. Thank you, friends. See you soon.